The last topic that I want to cover in this introduction to frequentist methods is about linear models. So linear models take us beyond the simple one sample t-test or the paired t-test. And two important things to understand about the linear model are the following. The first is when you have categorical predictors, like in my running example here, remember that in this example I have two conditions and I want to know if there is evidence against the null hypothesis of no difference between the two conditions. The dependent measure is reading time in milliseconds. So the two important things that I want to emphasize here are the following. The first is the contrast coding that you would use for the categorical predictors that we have in this particular example. Right? So if I have object gap and subject gap as the two condition levels, or whatever condition levels they are, you could choose what kind of contrast coding you're going to specify in the linear model. And the most common and the default contrast coding in R is the treatment contrast coding, which assigns 0 to one baseline level and 1 to the other level, which is called the treatment level. So, for example, in the example that I'm talking about right now, the Grodner and Gibson data set, you have two names for the categorical, the levels of the categorical predictor, object gap and subject gap. O comes before S alphabetically, so the alphabetically first level of this factor will be coded by default as 0, and the other factor will be coded as 1. So here's the output, which shows the default treatment contrast coding with the alphabetically first element coded as 0 and subject and the second element coded as the treatment contrast, right? So with this 0, 1 treatment contrast coding, the model looks like this, right? So the dependent variable is reading time. I have an intercept. There's a slope multiplied with either 0 or 1, depending on which level of the factor we have in every row of the data frame. And then there is a residual term, which is assumed to be normally distributed with mean 0 and standard deviation sigma, which is a parameter that we have to estimate. Okay. So what's interesting about the treatment contrast coding here is that the meaning of the intercept and slope actually depends on what is coded as 0 and what is coded as 1. If we have this contrast coding, object gaps coded as 0, subject gaps coded as 1, then the intercept has the interpretation that it's the expected reading time for the condition coded as 0 here, right? So if this level is coded as 0, this whole term becomes 0. The mean of the epsilon term here, the expected mean is 0. Therefore, the expected reading time for the baseline condition, which is coded 0, is the estimate for the intercept parameter. The slope parameter then is telling you the additional processing cost or reading time cost of reading the treatment condition, right? So that's the meaning of the intercept and slope in treatment contrast coding. Of course, you can reverse the order of the zeros and ones. So the baseline condition could be subject gaps and the treatment condition could be object gaps. In that case, the intercept would represent the estimate for the subject gap, and the slope would represent the additional cost of processing the object gap condition, right? So these were, of course, estimated from the data, and there you can see the estimates here for the default contrast coding here, the treatment coding. Here's the estimate for object gaps, and here's the speed up that you observe in subject gaps relative to the object gap, right? And then you see some statistical tests being carried out here, the t-test and the corresponding p-value. This model is, of course, wrong for the present data. Why? Because we have repeated measurements on from each subject for each condition. Even though this is the aggregated data, I'm working with the aggregated data here, I still have paired data, and that the repeated measures nature of the measurement here is not being reflected in this simple linear model. So that's why this model is actually wrong for this particular data, and I will just show you the correct version of this model on the aggregated data. But what's important to understand here is that this model is carrying out one important statistical hypothesis test, namely whether the slope is 0 or not. So it's testing the null hypothesis that the slope is 0, right? Which would tell you whether there's any evidence against the null hypothesis or not, that the slope is 0. That would be revealed by the statistical test that we do here. Okay. And of course, given the intercept and slope estimates, you can now derive the sample means for the object and subject gap conditions, right? For the object gap condition, which is coded 0, the intercept estimate gives you the estimated mean reading time. And for the subject gap condition, you would have the intercept plus the slope times 1, right? That would give me the estimated or the sample reading time for the subject gap condition, right? So this is how you can derive the estimated reading times for each of the two conditions from the treatment contrast coding. Okay. Now there are other contrast codings possible, and in the course we will discuss contrast coding in great detail, but right now I just want to introduce two very important cases. The second important case is the sum contrast coding. There what we do is, instead of having 0 and 1 coding, we code one condition as -1 and the other as +1. So which one you code as -1 and +1 is really up to you, but typically what I do is I decide on which one will be plus and which one will be -1 based on whether I expect the slope to be to represent a slowdown or a speed up. So I will just make that clear in a moment, right? So in sum coding, the two levels are coded +1, -1, or you could code them as +half, -half, right? That's just a scaling that one can do that would affect the slope parameter, as you will see in a moment. But the meaning of the contrast coding remains unchanged, whether you say +1, -1 or +half, -half. Both are sum contrast codings, right? So I will say much more about all that later on when we get to contrast coding, but right now this is all we need to know. And what changes, when you use sum contrast coding, an important change that happens is that the intercept now represents not one of the condition means, but the grand mean, the mean over both conditions, right? So the grand mean reading time is represented by the intercept, and the slope now represents the change from the grand mean in each of the two conditions. So what we are getting as a slope here is +51, right? So what that means is that if the grand mean is 420 milliseconds, if we go up +51 milliseconds, that is the estimated reading time for the condition coded +1. And if we go down, so if we go 420 minus 51 milliseconds, we end up with the estimated reading time for the condition that's coded as -1, right? So that's how you would interpret the slope now, as the deviation from the grand mean. Yeah? Now, you can also think of the slope parameter, the beta 1 parameter, as representing the following null hypothesis. The +1, -1 coding can be seen as representing the coefficients in the null hypothesis test, right? So basically the question we are asking with the null hypothesis test here is whether the difference between the two means of the two conditions is 0 or not, right? And that could be expressed as these coefficients here, which you can think of as being the coefficients that go into this +1, -1 coding, right? And of course, in this null hypothesis specification, if I had +half, -half, the null hypothesis does not change. That's scaled differently. So you could use +half, -half, or +1, -1 coding. Both would be some contrast codings, right? So that's the important thing to understand with some contrast coding. And you can now derive, for the condition coded as +1, you can derive the estimated reading time, like I mentioned earlier. And for the condition coded -1, you could take the intercept and slope and compute the estimated reading time for the condition coded -1. So that's how you would relate the intercept and slope to the condition means, for each of the two conditions. And this would depend on the contrast coding, treatment contrast or some contrast. In the end, the estimated reading time for the object gap and the subject gap would be the same regardless of what the contrast coding is. So what we say is that the contrast coding is actually reparameterizing the contrast. So the meaning of the intercept and the slope change depending on how you set up the contrast, but ultimately the hypothesis test being done is the same in these two cases. Okay, so that was one important thing I wanted to mention about linear models, the kind of contrast coding that you do. It's very important when you have more complex designs like a 2x2 design or something, or a 2x3 design, to start thinking seriously about what hypotheses you want to test and how those would translate into contrast coding, right? That can be worked out, as we will see in a later chapter. But it's important to understand these two types of contrast coding, treatment and some contrasts. The second important thing that I want to talk about in the context of linear models is the normality assumption. The normality assumption is actually not important if all you're doing with the linear model is estimating the parameters. Then the normality assumption is not of crucial importance. However, if you're carrying out a null hypothesis significance test, then the normality assumption should be approximately satisfied. Then it becomes much more important. This is discussed in mathematical statistics textbooks, so I won't dwell on this too much. I'm just telling this to you as a fact, but you can dig into this more deeply and read the literature on why what I said is true. So we can now fit a model, on the raw reading time, extract the residuals, right, from the linear model, and then plot the residuals graphically against the quantiles of the standard normal distribution. So what I've got on the x-axis is the quantiles of the standard normal distribution, and on the y-axis I have the residuals from the incorrectly fitted linear model, the model that is incorrect, but nevertheless I'm ignoring the fact that it's incorrect. I'm just demonstrating that you could extract the residuals from that model and compare it to a standard normal distribution, and what you would find, if the residuals in your model are approximately normal, then you would see the quantiles of the standard normal distribution aligning perfectly with the quantiles of the residuals in your data. And so this line would be diagonal across this range. So the fact that the line is not diagonal and there is a skew here is an indication that you have pretty severe non-normality in the residuals. Okay? So the normality assumption of the residuals is not being satisfied here. So if we were to take a log transform of the data, the model is still wrong, but now I'm just taking the log of the reading time. What that will do is it will downweight some extreme values in the data, and you see that the line, although it's still not at a 45 degrees angle as you would want it to be, it's certainly closer to that 45 degrees line, right? So you will never get exact normality of residuals, right? So that's why statistical tests like the Kolmogorov-Smirnov test or whatever, they're not super useful. What statisticians do is they just eyeball the residuals with this kind of plot, the QQ plot, and they check if the normality assumption is approximately satisfied, right? In the real world, you will never get exact normality, right? So we have to just live with the fact that satisfying the normality assumption approximately is about as good as it will get. Okay, so this is certainly better. We could probably improve on this, but this is good enough for now. Okay, so that's how one way in which you could deal with the violation of the normality assumption in your data, and that checking the normality assumption is important if you are doing hypothesis testing. If you're just doing estimation, then you could just do that without um, caring about the normality assumption not being satisfied. So until now, I've been showing you some linear models that were completely incorrect for the data that we have. And as I mentioned, the reason they are incorrect is that we have repeated measurements from each subject in each of the two conditions. Remember that in the aggregated data, I have 42 subjects and I have one aggregated data point for object gaps and one aggregated data point for subject gaps, but they're coming from the same subject. That's what I mean by repeated measurements. And so the way to deal with that in the linear modeling framework is to add an intercept adjustment by subject. So there's a grand mean intercept in the sum coded contrast, right? There is a grand mean intercept, and what we want is for each one of the 42 subjects, what I want to do is I want to assume that, so let's assume that we set up our model like this. So we have subject gaps and object gaps, right? And so let's just assume that these are our data, and this is coded as, I don't know, -1, +1. I'm just making this up. You can choose whatever contrast coding you want, but if you have like a difference like this, right? So this represents 0 here, right? And this would represent the grand mean intercept, beta sub 0, right? And so in the linear mixed model, what we're assuming is that each of the 42 subjects will have adjustments to this grand mean intercept value. So for example, one subject could be faster than normal on average. So this would be the adjustment. This would be the adjustment for that subject away from the grand mean. So what that would mean mathematically is that we would have a grand mean, right? Beta sub 0, and for that subject, call it subject 1, okay, let's say subject 1. For that subject, I would have an adjustment which I'll call U0 for subject 1, right? And this number, this numerical value would be negative because it's smaller than the average, right? So it's actually down adjusting the intercept for that particular subject. Similarly, if there's another subject called subject 2, let's say, right, who has a much slower than average reading time, for that subject, so I'm going to change this 1 to 2. For that subject, this number would be positive because it adjusts the intercept to a higher value for that subject. So that's called the varying intercepts linear mixed model, and it's written like is shown here in this syntax here with the LMER function, right? And this would be the correct way to analyze the aggregated data, okay? And what you will notice is that the output of this linear mixed model is exactly the same as the output of the pair t-test or the one sample t-test. Here's the t-value, which is exactly the same t-value that we had earlier. And you see that here, I reran the test here with the aggregated data, same t-value, right? So the varying intercepts by subject linear mixed model fitted on the aggregated data is going to be exactly the same thing mathematically as the pair t-test or the one sample t-test on the differences that I discussed earlier. Very important insight. So this was the varying intercepts linear mixed model fitted on the aggregated data, and one could look at the residuals of this model as before, and again you would see the characteristic skew on the raw reading times, which we know how to fix. We could use log RTs, and that would improve reduce the skewness in the residuals. Now, I just fit the model on the aggregated data by just adding varying intercepts by subject, but the correct way to analyze these data would be to work with the unaggregated data and to have not only varying intercepts by subject, but to have varying intercepts as well as varying slopes by subjects, and have varying intercepts and varying slopes by item. Right? So that would be the full, what they call the maximal linear mixed model by subjects and by items. Right? So this time we are not working with the aggregated data. We are working with the full data set where we have 8 data points from each of the 42 subjects in each of the 2 conditions. Right? So we have a total of 16 data points from each subject now, not 1 data point per condition from each subject. And so this model, what changes in this model is only the random effect structure here. Right? So what you can see here is that instead of having just one vertical bar subject as I had earlier for the varying intercepts model on the aggregated data, I have varying intercepts as well as varying slopes for subject, and varying intercepts and varying slopes for item as well, right? Because I have repeated measurements both on subjects and on items. And this is now operating on the entire data set, not the aggregated data anymore. What you'll find there is that so I'm fitting this model on log reading times, okay? You can see that here. Fitting it on log reading times. That's why my dependent measure is now the estimates of the intercept and slope are coming out on the log scale, right? So all that we will discuss later on when we get to linear modeling. But all I've done here is I've tried to reduce the skewness in the residuals so that I have approximately normal residuals, and that's why I took the log transform here. And so what's interesting for me here is the estimate of the intercept. This is the grand mean log milliseconds reading time, and this is the estimate of the slope, which tells me by how much the grand mean estimate has to be changed to get each of the 2 condition levels, which are coded plus half and minus half, right? What the intercept and slope adjustments are doing graphically is very straightforward. So drawing that plot again, right? So we've got, let's say, subject relatives, object relatives. These are our data and reading times here, right? And so suppose my intercept and slope look like this, right? So the intercept is this point here. That's the estimate of beta 0, right? And the slope is the slope of this line, okay? So what we are doing now with the by subject intercept and slope adjustments is that for every subject we have a different intercept, right? So just like before, we have adjustments to the intercept by subject, but we also have adjustments to the slope as well, right? So for example, it could happen that this subject, right, has a steeper slope than the average slope that we have here, and this subject here has a flatter slope compared to the average slope here, right? So what would happen is call this guy subject 2, call this guy subject 1. For this subject 2, I would have to have a positive adjustment to the average slope beta 1, right, to represent that subject's higher slope on in this line. And similarly, this person's slope is smaller than average, therefore I have to have a negative adjustment there. So mathematically what would happen now is that I would be fitting a model where I've got reading time or log reading time as my dependent variable, and I've got an intercept here, and I've got an adjustment to the intercept, which I call U0 by subjects. I index subjects with I, okay? That's my usual convention. Plus, I'm going to go to the new line here, and here, let me just keep going here. So, and then I have the slope. That's the average, that's the deviation from the grand mean by condition, and I'm going to adjust that slope by subject again. So I'm going to index the slope, call the slope adjustment U1, and I is the index on the subject, and the predictor here is the condition variable, which is coded plus minus 1 or plus minus half or whatever, right? So this intercept and slope adjustment is the innovation, in the linear mixed model, which allows you to take into account between subject variability in the intercepts and slopes. So the final point I want to make here is that this model here, with varying intercepts and varying slopes for subjects and varying intercepts and varying slopes for items, really looks like this. Okay, so it's important to know uh, where we are going with all this, because almost all the models that we are going to fit in the coming lectures will eventually have a structure that is analogous to the one that I'm discussing now, but maybe in just more complex settings, right? So this simple example with two conditions basically scales up to fairly complex designs, right? So what we had was grand mean intercept in the sum-coded contrast case with an intercept adjustment by subjects indexed by I, and a slope adjustment by items indexed by J, right? The items are indexed by J. Then I have a slope parameter, and the slope parameter is adjusted by subjects. Oh, sorry, it should not be 0. It should be U1 and index I for the subject ID, and they would be for items. There will also be a 1 with index J for the items, and then you have the predictor, which I'll just call condition, right? COND, and then the residual storm, right? That's what the model looks like. And so the important thing that I want to discuss here is the underlying assumptions about the intercepts and slopes for subjects and the intercepts and slopes for items, right? So the assumption here is that the intercepts and slopes adjustments for intercept and slope adjustments by subject are coming from a bivariate normal in this particular example, where each of the two random variables, or each of the two variables here, have a mean 0, and their variance structure in the bivariate context is expressed by a variance covariance matrix. This is all discussed in chapter 1 of the textbook. Right, so we are now assuming that the intercepts and slopes are coming from a bivariate normal with mean 0 for both of the U0 and U1, and a particular variance covariance matrix. The sigma U0 squared represents the variance of U0, and this one represents the variance of U1. This is the correlation between the two parameters, and this whole term here represents the covariance between them. So the correlation parameter is really telling you, graphically what it's telling you is the relationship between U0 and U1, right? So if the correlation is positive, what that means is that as U1 increases, as U0 increases, U1 also increases. That's the basic idea. If the correlation were negative, then that would mean that as U0 increases, U1 decreases, or if the correlation is 0, what that tells you is that there's no association between the U0 and U1. So that's the basic structure. The same setup holds for the W parameters here, or the W adjustments by item for the intercept and slope, but I won't write it out here because that would just make everything very complex here.